Hi, everybody, and welcome to Tuesday's session. Today we are in week 9. So we have progressed in this class a lot in terms of content. We are basically midway. We're ending today. We should be able to finish the solar system. And we'll start a series of chapters or units, I should say, dealing with light, because we're preparing for the second part of the third part, I should say, of the class, which deals with the stars and galaxies and the rest of the universe, basically. So you guys have already the review for the second midterm. It has been posted this week. It was supposed to be due on Wednesday, a week from today, October 19th. However, when I reviewed basically the content, I don't think that we will be able to be ready for the exam on Thursday next week. Therefore, next week is going to be a regular week. We will cover the units basically that we're supposed to be covering. And then the week after, of the 26th of October, of course, where the review will end. So you'll have more time now to complete the review and do it in your own leisure. I know it has more content this time around than the first time around. So there are more questions, more stuff that you need to go through, but you have now more time. Basically, you have more than it was a 10-day. Now it's actually what, 17 days or something like that, 16 days. Altogether, about slightly more than 2 weeks to go through the entire review and prepare it and be ready for the actual midterm 2, which is now planned for the 27th, meaning, of course, this Thursday is out of the question. We are still having regular class this Thursday, which is the 13th. Then the 20th, where we're supposed to have our second midterm, now the second midterm is actually the 27th. Does this make sense to you guys who are here? Okay, thank you, Chiara. So basically, the midterm plan, let me share with you the screen so that we are all on the same page. Again, this is what I was talking about in here. This is week 9, and I have posted the review for you guys. And the review, actually, I was thinking that maybe we could get all of these units today, and then some of the units, the other units, because they are really interconnected, units 22 and 23 and 24. It's the same idea, connected, dealing with light. And I was hoping to get them covered by next week, basically by Tuesday, a week from today. But then when I looked at the content, I really needed to give it a fair shake. I don't think it's a good idea to do that, because then we'll be squeezing a lot of materials, albeit these units 48 to 49, they're connected. 21, 22, and 23 and 24, they're connected. And since the midterm covers all the way to unit 24, then it doesn't make sense to basically rush through the content and then be tested on the Thursday after. So now I don't know about the homework 6, and it's still not published, as you can clearly see from here. So I still have to revise that. So basically, this is the content for next week, and then the content for the week after. Now I moved the midterm to week 11. Okay, so this is basically the plan, and hopefully you guys can are on board with it. You'll have more time actually to review, so that's actually good for you guys. And then that will give us enough time to go through everything in here. This week you have a quiz. Okay, you also have homework assignment also that popped up. Of course, you still have your discussion. You have stuff from the week before, and the review also that popped up also from this week. So there are a bunch of stuff that is going on for this week. So in terms of content, in terms of activities, in terms of assignments, so we have a bunch of things that are basically getting you ready to do the actual midterm. But the idea was the midterm was supposed to be next week, but if we put a lot of stuff right now, I don't think it's a good idea. When I looked at it again, I think the midterm will be ideal on the 27th, which means that the week after the 27th, that's the first week of November. Then the second week of November, the third week of November will be basically doing the stars and galaxies and things like that. And that will put us really, because then you have Thanksgiving week, and then the week after Thanksgiving, we will do our third midterm. And then immediately after that, the final, which is going to be the week after. So this is how the workflow of the course is. So, but before the 27th, during the week of the 27th, we'll be covering material that are dealing with the, so we'll get into unit 25, and there are another units as introducing from the 50s, the sun and the properties of the sun. So we'll be introducing some stuff from units from the other weeks. I'm going to move them in here. So yes, we're going to cover the materials leading to midterm, to this exam, midterm 2, hopefully by next week. And then we will, during the midterm week, we will start actually with the stars, because unit 25 is really an extension of unit 24 also, although I'm not including it in here in the exam because the exam will be too much as is, okay? So we will start the stars in here, and we'll continue with the rest of the weeks until we approach the final week. So this is the plan. So in terms of instruction, we still have this week, next week, and then the week after, which is where the second midterm is, and then the first 3 weeks of November. Then we have a week in between them, actually somewhere middle of November toward the end of November, and then whatever few days we have in November, that is actually going to be our last midterm. And then after that, the final, where we don't have instruction. So we'll try to cover a lot of materials during that time, so hopefully we'll be able to do everything we're supposed to be doing. So that's the plan. Okay, so that's where we stand on things. In terms of content also, I forgot to mention, and of course you guys are going through this thing, so you have the final observations for your lunar project this week. You have the assignment, which is due, you have a window for you to submit your report. You also have all of these discussions and all of these things that are part of your grade anyway in participation of the class. In addition to those who are sitting in Astronomy 125, who are doing the lab, we have also the weekly stuff that we do on Thursday. So that's the plan. So this week, Thursday, we have a class. Next Thursday also we have class. It's the Thursday after where we don't have a live class because we will have an exam, and that is October 27th. So this is just want to clarify it. And of course, it will follow up by more communications, basically announcements through Canvas, so that you guys are aware of what's going on. So let me share with you the content, share unit 48. And let me go to the top of the unit, the beginning of the unit, I should say. So again, we're talking in here about the ice worlds. And this includes some of the moons actually, because they are icy worlds too. So, but the focus really is on the dwarf planets, okay? And one of the moons, Neptune's moon, Triton, is actually an object of this classification, namely dwarf planet, that was captured by Neptune, of course, a long time ago. And we will postulate the reason why we think that is the case. Okay. As a matter of fact, any moon that has an irregular moon, I should say, whether in terms of composition, whether in terms of orbit, whether in terms of properties, then in this case, it's actually something that needs to be explained, and most likely it is a captured object, such as the case in this case of Triton. So what we're talking about in here are basically, first of all, we look into the 4 moons of Jupiter, the moon of Saturn. We're not going to focus too much on the moons of Uranus, because all of its moons are small, basically, relatively speaking. And then the big moon of Triton, which is what, the 7th or the 6th largest moon in the 7th largest moon in the solar system, after, of course, Ganymede, Callisto, Ganymede, Titan, the moon of Saturn, and then you have Callisto, the moon of Jupiter, then Io, the moon of Jupiter, then the Earth's moon, and then after that Europa, another moon of Jupiter, and finally, yes, it's the 7th moon, Triton, in terms of size in the solar system. It's still bigger than Pluto, okay? So it's a big moon, okay, Triton. And so we're going to talk about that. We're going to compare their geological processes on ice worlds, and you will see that their geology is driven by the cycle, by the water itself, basically freezing and evaporating when it's heat up, or erupting in some sort of a cryo volcanic activity. So that's basically where those worlds are. So like the volcanoes for the inner planets, where they are characterized by magma flow of extreme high temperatures, in those worlds, it's really the flow of water that causes the similar stuff, with the exception probably of Io. Io is super hot as is, and also erupts in sulfur-based volcanoes and all kinds of activities on its surface. Then we'll discuss the evidence for the existence of water in those icy worlds, because, hey, listen, we did not even land on some of these objects. We don't have probes on Europa, for example, yet we know it has an ocean surface underneath its icy crust. How do we know that? That's a good question you asked, okay? And it has to do with the properties of salt inside the water. Salt, which has sodium chloride, NaCl, the sodium that you have in your kitchen actually, is made up of sodium and chlorine. Sodium is a metal, okay? And metals have tendency to give up their electrons. So what happened in this case is, if the inside is hot enough, the water is in a liquid form, and if it's salty enough, that motion of Europa will cause what happened in here on Earth in terms of a magnetic field that the moon will have. So again, it's the salt present in that water. The water itself is really neutral. Water itself has no electrical properties. But if you put salt in, it becomes conductive. That's really why water is dangerous if you put an electrical cord that is live in it, because then it's going to conduct electricity. Not because water itself is, but because of the minerals inside of it, namely salt. So that's how we know actually that the moon has a salty ocean under its crust. Okay, similar to the ocean that we have in here in terms of composition. So that is actually a very, very interesting topic in itself, because now we know the moon has similar conditions and water into its under its crust, and not only just water, but more water than all the water on Earth. So it's an extremely, I mean, it has a lot of water under its crust, in addition to the crust that has also ice on it. And it's a super thick ice. I mean, trying to go and dig it and try to go into the ocean, to get into the ocean is extremely hard. It requires tremendous technology to do that. Fortunately, on the surface of Europa, that's the subject right now, is there are cracks. And you're asking, where did this crack come from? Well, they come from exactly the same point, since the water is under a lot of heat underneath because of the tidal friction, because how basically the Europa is under tremendous stress from the fact that it is not too far from Io itself, not too far from Ganymede on the other side, not too far from Callisto, although Callisto is a little bit far away from it. So it's between actually these two moons, Io on one side and Ganymede on the other side. But the biggest really player in the neighborhood is, of course, Jupiter itself. Okay, so it's being actually worked out all the time. So there is heat inside of its underneath of its surface, and that causes the water basically to become extremely hot, erupting in some sort of in the cracks that form on its surface. Okay. So if you look at Europa, and we're going to go through it right now, you will see that it doesn't exhibit on its outer surface as much craters as for example, the moon or Earth's moon does. Or even for that matter, for example, the surface of Callisto or the surface of even Ganymede. So it's not cratered as much. So suggesting that the surface is being all the time basically renewed through these processes of water basically going to the surface, erupting and forming all of these cracks. So that is an interesting topic by itself. And now there is actually very, very, very big interest in the moon Europa, because it has all the conditions for life. So scientists believe that Europa and it's inside its oceans, it has a marine life, most likely similar to the marine life that we have it on Earth, with the exception that that marine life does not get its energy from outside, from the surface of the oceans, because there is no access to it, but get it from the inside of the core itself, because it's hot. Similar to extreme, basically, conditions in the oceans on Earth, where there is life in there that does not rely on the source of energy from the sun, but rather from inside the Earth itself. So that is basically an interesting topic. And of course, it's not unique just to Europa. I mean, with the exception probably for Io, which probably is an exception completely because of its extreme hot conditions on the surface and also inside. The other moons also, especially Ganymede, it holds that similar potential. So Ganymede also have that similar potential. Callisto, not much. Callisto looks like it's kind of a world that quickly cooled because of it's far away from the moon, from the Jupiter itself. And it cooled to the point that it did not have a chance actually even to differentiate, in a sense that it does not have those layers, well-defined layers, as we see them in the case of the Earth, for example, the moon and the other objects, even the moons of Jupiter. So Callisto is probably an exception. The other interesting topic in here also is Titan. Titan, the moon of Saturn, which is the second largest moon in the solar system. It comes immediately after Ganymede in terms of size. And both these two moons are actually bigger than the planet Mercury itself, okay? And Titan also is an interesting object. Titan is the only object outside of, basically, in the outer, past the frost line, okay? Where we had actually a lander on it. So Titan, Huygens descended inside Titan and took pictures from the surface of Titan. And if you see any kind of movies or any kind of, basically even the pictures themselves, you will see, that's what we got still pictures, you will see what looks like lakes on its surface. Looks like rocks on its surface. And Titan is actually an interesting object in there because it has actually a liquid cycle on its surface similar to the liquid cycle on Earth, except the liquid cycle on Earth is driven by the water cycle. Namely, the water goes from frozen, then it's going to melt, and then when it melts, it's going to evaporate, and then it's going to rain again, and it goes through the process basically of evaporation, going in a liquid form, and basically, so that's the water cycle on Earth. On Titan, it has a similar process, with the exception that it's not water that is doing that. Actually, water is solid rocks. It's actually methane that is going through all of this cycle, basically from liquid to solid to gas. So, and it rains also. Okay, it rains actually on its. So those are the lakes that you see in there. They're actually methane. The surface itself also has favorable conditions in terms of pressure. It's not much different than the pressure you and I right now experience. So Titan itself is actually an interesting object on its own, because theoretically you could stand on its surface without having to suffer from excess pressure or actually lack thereof. But there's other problems actually with Titan, namely the fact that it doesn't have oxygen to begin with. It's mainly nitrogen, really, similar to the atmosphere on Earth, with the exception without much nitrogen in it. But of course, the temperature is tremendously cold, so cold that you really need to be warmed up. So that's the only exception on that moon. So again, Titan is actually a good candidate also for life, maybe not in a similar carbon-based life as we know it here on Earth, but actually maybe it's driven with similar processes, different processes that use different chemistry on its surface to basically harness the energy of the chemical reactions and basically grow and do whatever it wants to do. I mean, if you take living organisms from Titan, for example, if it exists, but this is a hypothesis, and you bring it, for example, on Earth, it will not survive. It's going to be basically deprived of its normal environment to do any kind of metabolism in the that it's accustomed to. So it's going to the same thing. You take an organism from Earth and you put it on the moon Titan, it's not going to survive also because of similar conditions. But so that actually Titan raises the possibility of another issue that actually lingering in the background. Not all life necessarily has to follow through the same form as we know it here on Earth. Life could have evolved with a different chemistry, with different requirements, with a different energy, basically intake, and it goes through the similar processes, grows, does all kinds of things similar to what we have here on Earth, but survives under different conditions in terms of temperature, in terms of gases that it needs to react with, and so on and so forth. If you take it and put it in different environments, it's not going to survive at all. So if it wants to probably inhabit another environment, it really wants that environment to be suitable to its own environment. So that's really what that Titan moon does raise for us. Obviously, if you are a fan of sci-fi, the movie Interstellar, if you guys saw it, they go and actually at the end of the movie, they go back to Titan. So that's what they end up with. Actually, the whole movie is about an anomaly somewhere near Saturn. And that is Titan, where the place is. So Titan has a lot of significance in here, and it's really an amazing thing. I know we are just barely ordered the telescopes, and we're hoping to get the telescopes next semester. So Titan is one of the fascinating things that when you look at Saturn itself, and you see its rings, and they're amazing, you see next to it a dot in there. That is really what captivates me always, is when I see Titan next to Saturn. So Titan is a big moon, and it's the second biggest moon in the solar system, and it's a moon of Saturn, and it has a lot of promises, a lot of things on its own, and it's a world by itself. Okay, Titan is not the only moon of Saturn, though. There are far more other moons that are of interest, but we're focusing in here on the big objects in the solar system, and here the icy objects. I already spoke about Triton, the moon of Neptune, which is bigger than even the dwarf planet Pluto, and the dwarf planet Pluto has its own story also going with it. Pluto itself is actually a universe by itself. It's a whole world by itself. Okay, being a dwarf planet, yes, it's smaller than, as I was saying in here, Triton, but it's still an interesting object by itself. It has a huge moon next to it, Charon. That's a big moon. It's not a small moon. And then in addition to that, it has 4 other moons, 2 of which were discovered in 2005, 2006, and 2 more recent ones. So if you look at the system where Pluto is, it's basically a whole world by itself. It has its own thing going for it. In terms of mass ratio between moon and planets, or a dwarf planet in this case, it is the biggest ratio. The moon Titan, the moon Charon, is so big that it doesn't really orbit Pluto. It orbits the barycenter, the center of mass between it and Pluto. The same thing, Pluto also orbits that point in here. So when the moon is on this side and the planet is on this side, they go like this, okay? So it doesn't orbit, unlike, for example, the case of the Earth and the moon really, yes, it orbits the barycenter, but the barycenter in this case is actually inside the Earth. Which brings me to another point of comparison in here, in that the ratio of mass, at least in size, between Earth and the moon is the next ratio after that of Pluto and its own moon. So it's really an interesting idea in here. That's why when we were talking about our moon, the Earth's moon, it was an oddity in a lot of respects. One of them is huge size, relatively speaking, compared to the size of the Earth. For example, if you take the biggest moon in the solar system, Ganymede, and you compare it to its own host planet, namely Jupiter, it's nothing. It's negligible, really. Same thing. If you take the second biggest moon in the solar system, namely Titan, and you compare it to its own host planet, which is in this case Saturn, well, it's nothing. Saturn is much, much, much bigger than the moon Titan. But the moon of the Earth compared to the Earth is a big ratio. Relatively speaking, of course, the Earth is still a lot bigger than the moon. Same thing. Charon, actually, relatively speaking, compared to Pluto, is the biggest ratio. That's why it does not orbit Pluto itself, but it orbits a point in between them, slightly off of Pluto, though. Okay. So that is another story. Another object in here of interest to us when we're studying these objects is Eris itself. Eris is the one that really caused mayhem in the solar system. Eris is a dwarf planet bigger than Pluto. And when it was discovered, it put a big puzzle. Should we, now do we have a 10th planet? Because at that point, Pluto was considered a planet. Are we going to consider now Eris planet? Because Eris is bigger. So now, if we're going to do that, now we have 10 planets. If Pluto is planet, Eris better be. And then not only Eris was discovered, Haumea was discovered, Makemake was, Quaoar was discovered. So a bunch of them started to pop up left and right. So at the end, they said, okay, you know what? This is too much. I mean, probably we will not remember all of these planets. So we're going to demote. We're going to come up with a new classification called a dwarf planet because they are big enough to be spherical in size. And in the case, for example, of some of them, they are interesting systems on their own, and they have their own moons, not just a moon, moons. So they have all kinds of geology on their surface, and they have all kinds of features on their surface that is of interest. But they are planets, but dwarf planets. And Pluto was actually put with them because, again, if Pluto is going to be retained as planet, at least Eris needs to be, because it's bigger, okay? So that is really what happened in this case. So we have now new classification, which is the dwarf planets, and the dwarf planets are rich in stories on their own. You take Haumea, for example. Let me go into the next slide because since I'm talking about the TNOs, trans-Neptunian objects. If you look at Haumea, for example, in here, Haumea is actually a, if you look at its shape, it has this egg-shaped structure, okay? By the way, a lot of these pictures in here, with the exception of Pluto and Charon, they're actually not, they're based on modeling, okay? Based on what we know. I don't, I mean, Charon, we took a picture of it, at least when the last mission went by it, and Pluto also, but not the other objects. But there's a lot of math suggesting how this is how their shapes are. So in other words, these are models really. But Haumea's shape is this way because it's spinning super fast, almost to the point where it's going to be torn apart into two pieces. So that's basically why its shape is elongated this way. And of course, Eris is in here. Eris is bigger than Pluto, and Makemake, Quaoar, and then you have Sedna, which is an object that is extremely elongated in this case. Out of all of this object, all of them are dwarf planets with the exception of Triton. Triton is actually a moon of Neptune. And again, these are the moons that I was talking about in here. The biggest moon, of course, is Ganymede. That's the third moon from Jupiter. If you start from Jupiter, Io is the closest. Then you have Europa. Europa is actually smaller than the Earth's moon, but bigger than Triton. And then this is the one that I was talking about in terms of interesting features and what we believe it probably has life inside of it. And then you have these two moons of Jupiter, namely Callisto, which is the furthest away moon from it. And then you have Ganymede, which is the third object. If you look closer to these two moons, at least for Callisto, it's highly cratered, suggesting its surface actually did not undergo a lot of changes on the surface. Titan, on the other hand, is covered. It looks like it's actually, it looks not too different from Venus when you look at it from outside, because of the fact that it has an atmosphere, and not a small atmosphere for that matter. It's a big atmosphere. So this is the stuff that is we're talking about in here. They're interesting objects in here. The temperature is super cold for all of these objects. Of course, the moon in here, the Earth's moon, is just put in here just for reference to see the sizes. That's all. Okay. And the fact that it's a big moon. So that's really what the comparison is in here too. So the temperatures in here for all of these moons are extremely cold. Obviously, Io in this case is an exception because its surface is extremely active at this point. It has a lot of volcanoes, okay? Take pictures of it today, come later, 3 months to 4 months from now, you're going to lose a volcano and have another one that pop up somewhere else. As a matter of fact, this is basically its surface right now. It has this extremely rich in sulfur. That's why it has this yellow color on its outer side. Okay, I forgot who said. I think it's Carl Sagan who said that it looks like it's a it's sick, you know, when a person is sick and the color changes and needs some penicillin, basically. That's what it needs, because that's basically what the color is. You know, when the sickness starts to ooze with all kinds of things, you know. So that's basically how the moon is. Again, the reason why it's doing sad is because it's squeezed all the time. Io is the closest, and for those of you sitting in Astronomy 125, this is an interesting object to remember, because not this, how is it? This lab. This lab is the one we're going to be, on Thursday, we're going to be measuring the mass of Jupiter by tracking Io, because Io is the closest moon to Jupiter. It goes around Jupiter in less than 2 days, basically. Yeah, 2 days is 48 hours. It's going to be about 42 hours or something going around the Jupiter, so it's super fast. To give us time to study it, we're going to take a telescope actually from Australia, and we're going to direct it to there using a computer, of course. So that's how we're going to control the telescope. And then we're going to track the position of the moon throughout the every 6 hours, basically, to see what it is. Based on that, we're going to use an interesting law that you guys are familiar with now, because we were tested on last time. And the law is the following. It says, basically, p squared is equal to a cubed, with the exception that p now is in years, and a is actually in astronomical units. Here is the deal with this expression here. This works for the Earth around the sun and planets around the sun. We're going to take this formula and use it for Io going around Jupiter. So there will be a constant in here that involves G, that involves the mass of Jupiter, and involves also 4 pi squared and so on and so forth. The 4 pi squared is just constant, and G is just a number. G is just a constant, 6.67 times 10 to the negative 11. What is the units for it? They are Newton meter squared per kilogram squared. I mean, forget about the units. It's not really that a big deal. So it's just a constant. But the point in here, we're going to be able to find the mass of Jupiter, because just by using this law in here, this is Kepler's third law. We're going to take this Kepler's third law, but in the version of Newton, to be able to find the mass of Jupiter for those sitting in Astronomy 125. If not, actually, the idea is based on this law, okay? So if you have had a chance to, even with a small enough telescope, an 8-inch telescope, the problem with an 8-inch telescope, you really need to have a tracking on it, okay? Because it needs to be motorized, and it needs to have the go-to technology, basically, where you're going to point it, ask where is Jupiter, it's going to give you Jupiter. Once you find it, it's going to lock itself on it. Otherwise, you're going to be moving the telescope around, because the Earth, remember, is spinning, okay? And if the Jupiter is out there, it's barely going to move, but the moon itself is going to be spinning, okay? Going around. So, but if you have it locked on Jupiter itself, and monitoring the moons around it and focusing just on Io by itself, you should be able to do this at home. You should be able to do this one even with an 8-inch telescope, even smaller than that, okay? You should be able to track that, but you really need to lock your telescope on Jupiter. Otherwise, you're going to have a nightmare, because every 6 hours, you're going to read the position of the moon. And again, you can only do a couple of observations at night. I mean, unless it's extremely dark region up in the northern, basically, places than where we are right now, 34 degrees in our latitude. So you really need to go higher in latitude to probably have extended nights, where you could do potentially 3 observations, but no more, because daylight will come up and basically ruin your observation. Obviously, for those who are sitting in Astronomy 125, we're going to be relying on a telescope that has clear view for an extended period of time. So we'll be collecting data every 6 hours and taking it and plotting it and finding the period for Jupiter, for Io around Jupiter, and estimating the distance and how far the Jupiter is in terms of the size of Jupiter itself. And based on that information, we're going to be able to find the mass of Jupiter. Does this sound interesting to you guys? Wait, Jupiter. It's like somebody asks you, okay, very good. Yeah, I mean, you will weigh Jupiter. It's the biggest planet in the solar system, much, 300 times more massive than the Earth. And you will say that I weighed Jupiter today. Okay, and that's how we're going to do it. That's the trick behind it, actually. We're going to rely on what we know from what we've learned, basically, up to this point. And that's how science really progresses. Okay, that's how we're going to learn things. Okay. Then I mentioned already in the introduction, Europa itself. This is why we think Europa has this. What is happening? Oh, it's moving in here already. Oh, it's in here. Sorry. Okay. So this is basically the ocean, and the reason is because of this. Okay. Liquid ocean under the ice. Okay. So that's basically what we think the surface of Europa is, okay? It has a metallic core, and it has this cracks on its surface. Again, the surface doesn't show a lot of craters, as I was saying, because the surface itself is highly active and being renewed all the time, and it's rich in minerals too, okay? And although it has a magnetic field, that magnetic field is weak, but that's actually signature coming from the fact that you have metals inside in here. You have conductors inside. And since the moon is spinning, and because the magnetic field is weak, so it gives the right proportions for how much salt you need in that water to really cause that weak magnetic field, okay? If you look at Ganymede and Callisto, they're a different story. First of all, Callisto, as I was saying in there, it's not as much differentiated. It cooled quickly, basically, relatively speaking. And it has a thin crust also, but its surface is heavily cratered, similar to that of the moon. Not that much really compared to the moon, but it's still cratered nonetheless, okay? And Ganymede seems to share some features with at least that's what we think. Okay, based on the models that we have, then Europa, including the surface itself, it has more actually resurfacing. It has more activity on its surface. So it looks like it's also going through a lot of stuff on it, similar to what's going on with the Europa, with the exception that it has more craters on its surface. Remember, it's further away from Jupiter. Okay, so it's not as much protected from the stuff as this Europa is from the craters. Titan is the other moon of Saturn, and that's the second moon in the solar system. And it has liquid methane and ethane on its surface, so it really has what looks like and it has also craters too on its surface. So it has a lot of features similar to the Earth. So it has atmosphere, mainly nitrogen, just like the Earth does, similar pressure, slightly higher more than the Earth, extremely cold compared to the Earth, 95 Kelvin. Remember, the Earth is 300 Kelvin. Right now, you and I are 300 Kelvin. So this is about 200 Kelvin below the Earth. It's about negative 200 degrees Celsius. So it's extremely cold. Okay, that's why the water on this surface is solid rock, as rock as it can get. Take a hammer and you try to break it, it's going to probably be extremely hard, okay? Because the temperature is extremely cold. But now this gases, they can actually go through the cycle of water in there, okay? And again, Huygens is the one that landed on its surface, and for several hours, for about an hour and a half, 90 minutes, it was broadcasting pictures and signal until basically it's come to the extreme cold temperatures on the surface. You not have enough battery really to do that. So these are the pictures that it sent, okay? This is on the way in, and this is right on the surface. If you look at this picture, it looks like a picture from somewhere on Earth, okay? Looks, as a matter of fact, somewhere from the Sahara Desert, okay? With the exception that this is not that hot, okay? This is extremely cold, okay? It's actually colder than the North Pole. So it's extremely cold surface in here. And those rocks in here, they're most likely that of water, H2O, which brings an interesting thing. And that's why it's interesting in terms of sci-fi movies and stuff like that, because you take this water and you break it into its, which is ice, you break it into its composition, and you can extract oxygen from it and you can breathe it. Not only that, but actually you can drink the water also before you extract the oxygen. So you can have a lot of stuff from the surface of Titan. So Titan seems to be a much better, actually much easier thing to work with than, for example, Mars, if you can get to it, because it's very far away. And if you can handle the cold. If you can manage the cold, which is probably the easiest thing to do, then in this case, you can have oxygen, you can have water, and you could survive in there, and probably some sort of a greenhouse in there. You can even grow your food and you're fine, okay? Because the pressure is not bad and everything else is not bad. The only problem is the temperature, okay? So that's why we actually sent a lander on its surface, because of a lot of promises that that moon has. That's Titan, the moon of. So Earth 2.0 actually is not Mars, it's not Venus, it's most likely, if we're going to be able to do it, it's this one, the moon Titan. Okay. Titan, as I was saying in here, is actually, if you look at the pictures in here, it looks similar to that of actually Pluto itself. Okay, so it's slightly larger than Pluto, but smaller than Europa. Europa, remember, is smaller than the Earth's moon. So, and it orbits backward relative to Neptune's rotation. So because of this discrepancy, that's why we believe this moon is not a moon that formed. It's not really, it was captured by Neptune itself, okay? So that's the story behind it. And it has similar stuff, similar to Pluto itself. It brings us to Pluto now. So again, in 2015, at about 50,000 miles per hour when it went through it, it took a lot of pictures in here. Okay, and then it has also shown the cycles of, again, the methane and nitrogen and carbon monoxide. Water is actually, again, if it is involved again, water is involved in some sort of a volcanic activity. So that's basically similar to that. The temperature is extremely cold on the surface, so the surface itself. And it has some features at this point that are kind of interesting. We're trying to understand, I mean, the scientists trying to understand them, including this color, which looks like it's a brownish color, which is made up of some sort of an organic matter, not necessarily of living organisms, but it could have been organic, I mean, from organic chemistry that is based on the hydrocarbons, and hydrocarbons are all organic. So that you guys know what the hydrocarbons are, it's a combination of water, I mean, not water, hydrogen and carbon. For example, CH4 is methane, okay? So that is actually an organic matter, although it can form in a non-organic way. Same thing, for example, in other combination of carbon and hydrogen, sometimes even oxygen and nitrogen, okay? So that's really all of the main components of organic matter, you and I, and all of the living organisms, including plants and animals. Again, it's Moon Charon, and then 4 other moons were discovered. 2 moons, first of all, in 2005, 2006, Nix and Hydra, and then 2011, 2012, we have the other 2 moons, Kerberos and Styx. So for a total of 5 moons, because remember it has Charon that was discovered immediately after Pluto was discovered because of the wobbling motion that Pluto was exhibiting. So it's a relatively very, very big moon compared to anything in the solar system. Okay, the highest relative mass of any known moon. Pluto and Charon orbit a common center of mass, almost a double dwarf planet. So it's almost like a binary dwarf planet. Okay. Although the center of mass is a lot closer to Pluto than the moon itself. Now, which brings us to its orbit. The orbit of Pluto is really kind of eccentric a little bit, in a sense that it has a higher eccentricity. At some point, it brings it very close from Neptune, and at other points, it's going to bring it very far away from Neptune. But the orbit of Neptune, when it's very close from it, Neptune is not in that neighborhood. This is how we think, actually, Triton was captured too, because it went too close from Neptune, and Neptune is big enough and massive enough, so it's captured it over time. So that's basically what's going on with the case of Pluto. And Pluto is not the only object past Neptune. As a matter of fact, we have a new classifications called the TNOs. The TNO is trans-Neptunian object, and it includes a bunch of stuff, including Pluto, by the way. So Pluto, Orcus, Eris, Sedna, Makemake, Haumea, and Sedna's orbit is extremely eccentric, okay? Quaoar, and then Eris. Did I mention Eris? Yeah, Eris is in here too, okay? So again, when scientists looked at this one, and this is actually a recent discovery, they saw that there is some sort of a weird behavior of all of these TNOs. They seem to be influenced by another object out there, okay? And that object that is out there is big, it's massive, and it's just right, it needs to be in the right position to be able to basically alter all of this object's motion around past Neptune. So remember, Neptune's orbit is way, way, way inside in here. We're looking at a scale that is ridiculous at this point. So the Earth, you cannot even see it. Jupiter, you cannot see it. So Neptune is way inside in here, and we're looking at objects that are very far away. At this point, they don't have a name. They're just called, Sedna is one of them, actually. Now, their orbit seems to be influenced by another object that is out there. And according to all of the models, basically, there must be a planet big enough that disrupts their paths and give them this some sort of a unique behavior. If you put that planet in this orbit, then everything fits beautifully. So now, basically, the models suggest that there must be another planet out in the solar system. And it's a big planet. It's not a small planet. Several times bigger than the Earth is. So, and this planet must be very far away. Look at the distance. I mean, Neptune, which was discovered by math, really, is very close from the sun, relatively speaking. Okay? Neptune, which is about 30 astronomical units right now, is very close, relatively speaking, compared to this planet 9. So hypothetical planet 9 is still something that we're looking for in terms of all of astronomers right now. They're hunting for it. You're looking for something that does not emit light, number one. Number two, hopefully it's on the ecliptic, because it's a big planet, so it must be on the ecliptic. Same plane. So that gives you at least a range where you're going to be looking at. But then that even for a half-degree variation, because of the extreme distance, you're looking at a large amount of space to look for. So a lot of telescopes are looking out there, trying to find it. And if you find it, probably you can name it too, as long as you submit a name, and then hopefully astronomical units will accept it. So again, this is the story with planet 9. So it's really a hypothetical planet right now. It does not have a name yet because we have 8 planets. So we call this planet 9, okay? There were attempts initially to call it planet X, but planet X was actually planet Pluto, because Pluto at some point was called planet X because people actually believed that it existed before it was discovered. And there was a hunt for this planet for Pluto, because initial calculations for the orbit of Neptune had people believe that there must be a big planet out there, and they called it planet X, and they were looking for planet X for a long, long time until Pluto was discovered. So when Pluto was discovered, it turns out its mass is a lot smaller than that of the Earth and did not fit the bill correctly. So when the numbers were revised, there were errors actually in the calculations of the orbit of Neptune. So those errors, people thought, okay, maybe we have another planet, but it turns out we really had another planet, except that that other planet was not due to was not causing any disruption in the orbit of Neptune, but it was discovered, and a bunch of other dwarf planets were discovered later on. So in terms of sizes of the trans-Neptunian objects, or the TNOs, again, Eris is bigger, both in size, about 300 kilometers in diameter bigger than Pluto. And in terms of mass also, 1.7 versus 1.3, okay? So it's actually a big planet, okay? Its orbit, though, of Eris is far away from the it's almost time and a half, actually, more than a time and a half, far away from the sun than Pluto. Remember, Pluto is 40 astronomical units, very far. And this guy is 67, 68 astronomical units. And the eccentricity, which is really an important number in here, how eccentric. Remember, when the eccentricity is 0, the orbit is circular. But the eccentricity now, it's much, much bigger than 0. Obviously, it's not that big, you're saying. But look at Sedna. It's almost 1. 1 is a line. So Sedna's orbit is like this. If the sun is here, obviously, when it's very close from the sun, it's still far away. It's about 80 astronomical units. Something. Okay. No, it's about 50 astronomical units. So it's still further away from no. And then when it's far away from the sun, it's very far. Okay. So that's really the point in here with this planet. Obviously, Pluto is eccentric, but it's not that eccentric compared to Eris. And Makemake is a little bit more circular than the others. Quasar actually has a more regular path. It's almost a circle. And then Orcus is similar to Pluto. Actually, it's opposite to Pluto. It's almost on the same path, with the exception that one of them is on this side, the other one is on the other side, and they keep on chasing one another. Okay. So this is the orbits of this planet. As a matter of fact, if you look at the distance from the sun to Orcus, it's the same distance as Pluto is. So here is the sun. Here is where Orcus is. Here is where Pluto is. And they keep on sweeping, chasing one another, on opposite sides from the path. Okay. That's basically what Orcus is and Pluto is. So it's really interesting studies in here, all of these things, okay? We spent almost, so let me stop sharing in here and see how much we have and how much we can cover, honestly, see if we can really give it a fair shake if we're going to do the other unit, namely 49. Okay, let me give a brief introduction to Unit 49, and then we're going to come next time and discuss it. So Unit 49 deals mainly with comets, okay? And comets and some of the other features in the solar system. So comets are interesting objects because they are actually the object that carry a lot of materials into the planets. We believe a lot of the water that is on the Earth and actually on all of the other planets and moons most likely came from comets, because comets, they form in very far reaches of the solar system. That is when H2O solidifies and becomes a rock. Not when the Earth was forming in the beginning and then somehow it was extremely hot. How is it going to have water in it? It was super hot. So if there was water in there, it has evaporated, broken down into its components. Hydrogen went one way, oxygen went the other way. Hydrogen is a lot lighter. Most likely, is going to be escaping from the planet completely, because it's moving super fast compared to when those temperatures were very high. And the oxygen is probably also, for a lot of parts, is going to escape too, and the remaining will combine with the other metals and form all kinds of oxides. So that's the original water, if in case it existed in the case of the Earth or any other planet for that matter when it was forming. But the planetesimals that formed far away from the sun, those, they're too small and the water froze. So now, after the solar system formed and after the planets really formed and they started to cool down, here comes the comet in here with tremendous amount of velocity, and they impact the planets and they deliver their content. And that's how the water on Earth, or even that of all of the other planets, including Venus, including the moons and everything else, we think that how the water on the surfaces of all of these objects basically came to be. So if you think about it, it's really life on Earth really owes its existence to this object named the comets. So what the comets are, there are two types. The comets that have a short path, basically a low, smaller radius, if you wish, distance from the sun. Those, they go only so much around the sun and they evaporate because of the fact that They're water actually, and every time they come close from the sun, the temperature increases, and once it increases, they form the tail, and that coma that forms has actually two components in it. It has the gas, which is the evaporated liquid that was on its surface, and as it evaporates, it's going to form a trail behind it. But then the radiation from the sun is hot enough that ionize some of them, and there will be two tails, a blue one and actually the white one that is behind the planet. This extends for a long, long distance, hundreds of thousands of kilometers. As a matter of fact, the entire comet can have, with the nucleus, which is the bulk of the stuff inside. So if this thing goes around several times around the sun, after a while, it's going to lose materials, because that material is going to be left out. As the planet later on, as a comet later on moves away from the sun, it's going to cool again, and it's going to freeze again. It becomes a solid rock again. But then it's going to come back again and evaporate. And as it does, it evaporates, it leaves behind it those materials. If those comets happen to be in the same orbit of the Earth, as the Earth is orbiting the sun, it goes through the leftover, the dust that was left out. That dust, when the Earth is going through it, will enter the atmosphere of the Earth and form those showers, the meteorite showers that you see in, for example, December, all kinds of meteorites. Those are the ones that come to us, okay? And they look like they're coming from specific constellations. Now, if they're short, if it's short distance, the comet is going to die out. So it was actually Mr. Oort who suggested that these comets that are still going on right now, they must be coming from a very far away region, that it takes a long time for them to orbit the sun. When they pass by the sun, then they take a long time to come back. So these objects, they're coming very far away, either from the Kuiper belt itself or from what is now known as the Oort cloud, okay? And those have a very, very long, basically, period, so that they can come and raise the sun and so on and so forth. So when they reach the frost line, which is about 4 or 5 astronomical units, which is the distance from Jupiter, they start to heat up, gain heat. So their surface temperature starts to increase, meaning the gas starts to evaporate, and they start developing the tail. And as they go around the sun, the tail develops further, and that's what you see outside on the night sky, that beautiful tail that forms for the comets. The comet comes back on the other side from the sun and goes again, and when it passes that distance, it's going to start freezing again and forming the solid rock that it was to begin with, and the cyclopes, okay? So that's how comets are. And that's the hypothesis for them. And we're going to come next time on Thursday, same time. We're going to finish this topic and hopefully even start Unit 21, which deals with electricity. Sounds like it's a good plan, guys? Yes? Okay, very good. Thank you very much. Thank you, guys. Okay, so I'm going to stop the recording, and I will see you guys on Thursday, same time.